All right. Thanks, everyone, for being here. My name is Tim Walsworth. I'm an assistant professor of fish ecology and fisheries management at Utah State University. And Kevin just gave a great kind of introduction to the monitoring we do on Utah Lake. I'm going to talk a bit about how we estimate the response of carp to these removal efforts. So Kevin stole a bit of my thunder with his, so I'll go through this really quickly. Just reiterate, so carp were introduced into Utah Lake in the late 1800s as a food source to replace over-harvested native fishes. They were introduced globally, many lakes and rivers around the globe. But we now know, and they're now considered one of the worst invasive species globally, and in Utah Lake, they accounted for over 90% of the fish biomass that would be caught in nets in the early 2000s. We also know they have a lot of negative ecosystem impacts from their benthic foraging behavior, where they uproot vegetation, they stir up sediments, they can grow really fast, they can compete really well with native fishes and cause all sorts of changes. So because of these changes and their impacts on the habitat and prey availability for June sucker, the June sucker recovery implementation program implemented a mechanical removal effort in 2009. So this mechanical removal, we go in with nets, catch the fish, pull them out. Started in 2009 and is largely with commercial beach seines through about 2023. And then the last couple of years, there's been a couple of pilot studies with these baited box traps. The goal for these removal efforts was a 75% reduction in biomass from the start. And they're really successful at pulling lots of carp out of the lake. We have over 13,000 tons of carp. It's about 30 million pounds of carp throughout that time. But it's always important to remember that removing carp isn't the goal of the carp removal program. The goal of the carp removal program is to reduce the effects of carp in the lake. And that requires reducing the amount of biomass of carp out in the lake. So since about 2018, we've been working on this carp population model and updating it every year, where we estimate how the carp population has responded to those removal efforts, not just what are we catching, what's the remaining population look like after those removal efforts. So here we're going to talk a bit about how the carp population biomass has changed in response to historical removal efforts and whether or not we've gotten to that target. This brings me to one of my favorite quotes about fisheries management. That's from a professor at the University of Southampton in the 1970s, John Shepard. It says, "Managing fisheries is hard. It's like managing a forest in which the trees are invisible and they keep moving." And if we look out across Utah Lake, we see it's a big lake, can't see any carp, we know they're all there. And even if we look at our data, if we go in and haul a big net of fish out, you see there's still some invisible fish there. We catch a lot of these big adult carp. So here we have two figures of two different gear types of length. So carp, individual carp length on the x-axis, and then the number caught on the y. For years, the gears have mostly caught these big, large carp. We don't see the small carp. However, if we think about how populations work, in order for there to be big adult carp, they have to have been there as small carp at some point. So the small carp have to be there. And so this allows us to estimate abundance through something called a statistical catch at age model. We have catch each year of fish of different size classes in Utah Lake, because again, we don't catch those small fish. We really only see the older age classes. You do this through enough years, we know that age zeros in year one will be age one in year two, age ones will be age two in the next year, kind of move on. And because of this, we can estimate the abundance of these young age classes in previous years based on how many older fish we catch later on. And so using data from the commercial fisheries removal program and standardized surveys we've been running in conjunction with UDWR, the commercial fishers and June sucker program, we were able to generate estimates of abundance across all the age classes in the lake. And from that, we can estimate these biomass trends across time. So as Kevin showed in his presentation, see a strong decline in carp biomass in the early years of the removal program through about 2017, 2018, where it's stabilized. It remained pretty low 2016 to 2019 and slowly been creeping up since then. So the carp are estimated to still be below that starting biomass but above where we'd like them to be. As Kevin mentioned, we have the data from this year. We're currently updating these models with the newest estimates. These results kind of raise the question, though, what has caused the decline in biomass to pause or to stall out? What challenges has this removal program faced? One of the issues is just the scale of Utah Lake. Utah Lake's one of the largest lakes in the world by surface area, and because it's so shallow, the whole lake is really pretty good carp habitat. The largest successful carp removal in the world was in a lake about 1/7 the size of Utah Lake, and they had a pretty similar budget to what the carp removal program Utah Lake used in order to do that. Generally, we see with invasive species that productive populations in large ecosystems are more resistant and resilient to removal efforts and control efforts. So you can expend a large amount of effort and have really little long-term impact on those systems. So the scale of the system is really, really tough. And therefore, successful control in Utah Lake is likely going to require quite a bit more investment in removal efforts. The selective gears are another challenge that's faced by the program. So I mentioned earlier, we only really see these older age classes in the data set. The difficulty catching these smaller individuals is a real challenge because some of those age classes we don't see in the data set are already sexually mature and therefore reproducing, which means there's this pool of reproducing carp out there that we're just not seeing. Previous graduate student in the lab did some analyses, and if you were able to remove those smaller but still mature age classes, the level of increased effort you would need to successfully control the population would decline quite a bit. Kevin talked quite a bit about these fluctuating lake levels we see in Utah Lake. That's a big problem for carp removal as well. So these periodic elevated lake level periods are kind of have two negative effects for carp removal. First, carp recruit better when the lake is high. There's more habitat for their juveniles to rear in. There's more spawning habitat for them. There's they're in lower densities that they're able to spread out, so more food for each individual offspring. And so we see these periodic periods of high recruitment when the lake comes up. High lake levels also make the gear that's been used historically less efficient. We use those big seines that are really effective. You can drag them through open water areas. As soon as you get a lot of vegetation you're trying to pull through when the lake is high, the nets get lifted up by the vegetation, you drag it over, or they get tangled and you can't effectively close it. So high lake levels are both increasing the productivity of carp and reducing the effectiveness of those historic removal efforts. And lastly, there's economic challenges. So as biomass of carp is reduced, the catch rates we see per unit of effort, so per haul of a net, go down. There's just fewer fish out there in lower densities. We can catch fewer fish per effort. The cost of doing each of those units of effort stays the same, though. Therefore, the cost per pound we remove starts going way up as biomass goes down. And this is a challenge, particularly for doing this for through a commercial fishery approach. Those fishers, the cost per pound they're removing is going way up, and if they're not getting higher prices per pound, they're not going to be able to make money and stay in the fishery. It also indicates that maintenance costs, so once we can reduce it low enough, maintaining it really low is going to be expensive. It's going to be hard to keep catching fish when they're at low levels. And if we have the goal of eradication of carp, it's going to get even more expensive at those lower levels of carp. There are studies that have shown over 95% of eradication programs for some species occur trying to remove the last 1% of the population. So this low biomass period is the really hard part to deal with. So moving forward, what we've been working on are using this population model we fit to the data that we see in the lake to explore these kind of what-if scenarios. What if we increase the amount of harvesting effort? What if we try some of these hypothetical or novel technologies that are being developed out there, like Trojan Y chromosome carp stocking? And we've explored these for the past couple years. Looked at Trojan Y chromosome stocking, looked at targeted poison baits, how much would you need for that to work? Increasing the scale of mechanical removal efforts, so just doubling, multiplying by 10 the mechanical removal efforts and seeing how that works. One project we've just started recently with a new graduate student is examining dynamic pricing for a commercial fishery. How much would you need to pay per pound to keep fishers, commercial fishers exerting effort in the fishery if we want to collapse the fishery through commercial fishing? What we know from fisheries globally, if they're worth money, we can collapse them. We've done it over and over again around the globe. So if there's a way we can pay for, make carp worth some money, fishermen will go out and get them. Just got to figure out what's that cost going to be, what's that going to scale up to. And we're also just continuing our monitoring efforts to see how the ecosystem is responding, because again, the goal is not just to get rid of carp. We want to see the ecosystem rebound and see more aquatic vegetation, more recruitment of wild June sucker. So again, we can use our model to assess some of these hypothetical as well as currently available methods. So over on the top right, we've got an assessment of if we just increased historical seining methods, how much we need to increase them to achieve our target in the long term, and it comes out somewhere between 5 and 10 times historic effort, and a lot of that's going to happen when the carp biomass is low, when our catch goes down. It gets really hard to catch them, so you just need to increase effort more. We've also found for a number of these alternatives, like target poison baits, you can put a whole lot of effort in, so put a whole lot of targeted poison bait out there and have very little long-term impact until you hit some threshold, and then you start seeing a sustained long-term effect. Because it's a big ecosystem, carp are really productive, they can bounce back pretty quick. But again, the model allows us to try all these things out, share it with June Sucker Program, UDWR, UDWQ, and help them inform their management going forward. But from all the analyses we've done thus far, they've all suggested controlling carp effectively requires a substantial increase in effort or investment levels. And with that, I'm happy to take any questions. Oh, Q&A. Okay, yeah.